Okay, so nothing that we're doing today is crazy new. I think that the seniors will be okay without it, but if not, they're going to have to watch the video. All right, so toolkit page 1. Simplifying radicals. Now, you have to be able to simplify a radical to do a lot of things. We're going to be working with right triangles, so we're going to use Pythagorean theorem, and sometimes in Pythagorean theorem you end up with a root and you have to simplify that root. You've simplified radicals when you end up with quadratic formula and a root. So like the actual concept of simplifying radicals applies to a lot of the units, but it's really big in the trig unit because it happens a lot with triangles, and trig has a lot to do with triangles. So just the steps in case you forget. You check it in the home screen. So like if I type the square root of 36 in the home screen and I get a whole number, then I'm good to go, right? And if in the home screen I get a decimal, then I go to the y equals screen and I do the number divided by x. So in my home screen of my calculator, if I want to check the square root of 36, hopefully you know what the square root of 36 is, all right? But still, you can check it. And if when you type it in the home screen you get a whole number, then that's just your answer. So the square root of 36 is just 6. Now when I go to do that for the square root of 27, I get a decimal. If you get a decimal for that square root, you want to be able to break that square root up. So we go to the y equals screen and we do 27 divided by x. And what I'm looking for in this table is a perfect square. So on your toolkits at the top it says perfect squares. The first perfect square is 2 times 2, and then 3 times 3, and then 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12. I'm going to stop at 13 times 13. But it keeps going. All right. So what I'm looking for in my y equals 27 divided by x table is I'm looking for one of those numbers. Obviously, it's not going to be a number bigger than 27. So I'm really looking for 4, 9, 16, or 25. Those are the only possibilities. So if you look in the table, for a 4, 9, 16, or 25, you see a 9. Next to the 9 is a 3. So I'm going to break this 27 up into the 9 and the number next to it. And then you could check each of them individually. Sometimes with my freshmen, they screw up which one comes out of the root and which one stays in. And so they say the answer is like 3 root 9. So I just tell them, like, make sure you check root 9 and root 3. One of them changes and one of them's a funky decimal. Keep the funky decimal under the root. Right, so the 3 staying under the root, the 9's coming out of it. So this is like 3 root 3. All right, so as you've been refreshed on that, I'm going to have you just try number 3 here. So you're going to do the 162. See if you can break that up. You're going to need a calculator. And yes, you don't know the perfect square that goes into 162 off the top of your head. .162 itself is not a perfect square. It doesn't show up on the perfect square list. So you're going to have to go to your calculator. Y equals 162 divided by x. And you're looking for the highest perfect square that goes into it. What's the highest perfect square that goes into 162? 3 and 18. Oh, 9 square root 18?
No, it's 9 and then
I think there's a bigger one than 9. 81. 81 goes into 162. And next to the 81 is a 2. So 81 and 2. And then the square root of 81 is 9. So my answer that I'm looking for here is 9 square root of 2. All right. Now, what's different about number 4 is there's this thing called a coefficient. There's a number in front. It really doesn't change what I'm doing with the problem. I'm going to ignore the coefficient and I'm just going to look at the 48. 48 is not a perfect square. So I wanna see if there's anything that is a perfect square that's also divisible by 48. My recommendation, especially if you're picking the lower perfect square, is start on this side. Start with the 48 and work your way down the list. Because if you start with the 1 and work your way up the list, you're gonna pick the lowest perfect square, which is 4. But if you start with 48 and work your way down the list, you'll pick the highest, which is 16. Alright, so I always start on this side. So I'm gonna use 16 and 3. And that's gonna break up the 48, but it's not gonna do anything with the 2. The 2 just stays in the front. And the square root of 16 is 4, so this problem becomes 2 times 4 root 3. And then I just do 2 times 4. So this is 8 root 3. So coefficient just kind of carries its way all the way through the problem until the very end. Alright, so when you are multiplying radicals, which is numbers 5 through 8, you want to combine your like terms before you simplify the radical. You're going to save yourself some work. Like rather than reduce this radical, now combine them and reduce again, just combine them all in the start and then reduce. Then you're only reducing in one step. So since 3 and 6 are both under radicals, they're both under roots, they're called like terms. So I can do 3 times 6, which is 18, and then because both of those numbers are under roots, I can just keep it under the root. So I'm just doing multiplication for those. And now it just becomes just like we did before. Like I would go to my y equals screen, I would do 18 divided by x, and I would look for perfect squares that are divisible by 18, which is 9. So this is 9 and 2. So 3 root 2. Alright, so we're combining like terms. In order for them to be like terms, they have to be in the same format. So like I can combine the roots here, but this 2 in front, I can't combine that with anything. So I'm just gonna leave that green 2 the same. So the coefficient is 2, and then 2 times 2, root 2 times root 2 is root 4. I'm just multiplying those common terms. And the square root of 4 is just 2, so this problem becomes 2 times 2, which is 4. It's all about combining your like terms. So if they're outside of the root, they're considered like terms. And if they're inside of the root, they're considered like terms. So negative 4 times 5 is negative 20. And 6 times 12 is 72. So root 6 times root 12 is root 72. So I'm just combining them to one root. Now that I have it as one root, I need to check it. I didn't have to do that here because the root itself was a perfect square. But here I'm going to have to go check 72 out for a perfect square factor. So I'm looking for a perfect square of 36. I'm going to go this way rather than this way. This way you're going to pick 4 and 18. But this way you're going to pick 36 and 2. 36 is the bigger perfect square. So I'm going to keep the coefficient and I'm going to break that 72 up into 36 and 2. And the square root of 36 is just 6. So this problem really just becomes negative 20 times 6. You're multiplying those numbers in front. So this is negative 120 root 2. Alright, so it's root So it's root times root for that last one. So the 5 times the 5, and then there is technically a coefficient in that front. So I'm gonna do these. And then even though this is just a minus sign, it's kind of like a -1. So I am gonna multiply -1 times 7. So -1 times 7 is gonna make the coefficient in the front be -7. And √5 times √5 is √25. So this becomes -7 times 5. Or -35. I think there's one more for you to try, so take a moment, try this next one, number 9, before we start looking at the conjugates. Alright, so what do we get when we combine like terms here? What's the coefficient in the front become? -3. And then what about the root? 3,200. Alright, so that definitely splits up. What perfect square goes into 3,200? I think 1,600 is a perfect square. Let me just check. Thinking because 16 is a perfect square and 100 is a perfect square, then 1,600 is probably a perfect square. It is. Alright. So I am using, I think actually there even is a bigger one though, is there? 1,602? That's about right. Alright, so the square root of 1,600 is 40. And so this becomes 40 times 3, so -120. Root 2. The next two here are called conjugates. What makes something a conjugate is the first number in the quantity is the same, and the second number is opposite. This is like differences of perfect squares. X plus 5, x minus 5 is a conjugate. The first term, x, is the same. The second term, plus 5 minus 5, are opposite. Conjugates, think of differences of perfect squares. Like when I factor something that's a difference of perfect squares, it doesn't have a middle term, right? Like x squared minus 4 has no linear term. So if you multiply conjugates, you'll cancel out the middle term. And you'll see that. We're going to FOIL this out, and you'll see that the middle term cancels out. But anytime you multiply a pair of conjugates, the middle term, the linear term, will become 0. So like if I were to FOIL this, I would do 2 times 2, right? So that's 4. And then I would do 2 times -√6. And the way that I would write that is -2 root 6. All right, and then I would do 6 root 6 times 2, and that's a positive, so that would become a positive 2 times root 6. And then positive root 6 times negative root 6. So the positive in front is like a positive 1, and the negative in front is like a negative 1. So the coefficients are positive 1 times negative 1, which gives me a negative. And root 6 times root 6 is root 36 when I'm multiplying them. What happens here is these two terms zero out, because if I have 2 root 6 and I take away 2 root 6, that whole term is 0. So what I'm left with is 4, this cancels out, and then minus root 36, but the square root of 36 is 6. So I end up with 4 minus 6, and 4 minus 6 is negative 2. So it doesn't look like that is going to simplify to something simple, but it does. And it does because it's a conjugate. Conjugates will always work out where that middle term simplifies, and so that square root will disappear. All right, so these are considered conjugates because the first number matches and the second number's opposite. If this was like 4 plus root 20, 4 minus root 15, it's not a conjugate, okay? They have to be the same number. Second number has to be opposite. So if I were to FOIL this, I would get 4 times 4, and 4 times negative root 20 would become negative 4 root 20. Just bringing the minus down, I'm making the 4 the coefficient on the 20. And then positive root 20 times 4 is positive 4 root 20. And positive root 20 times negative. The positive times the negative gives me a negative. And 20 times 20 is 400. So I get a root 400 there. What happens here, because they're conjugates, is the negative 4 root 20 and the positive 4 root 20 zero out. And I'm just left with 16 minus the square root of 400. The square root of 400 is 20. Like if you typed that into your calculator, it's just 20. And so ultimately, I just end up with negative 4. Now the answer's not always negative. It just depends on what numbers you're working with. But you should end up with just a number when you're multiplying the conjugates. You okay with that? All right, so in your workbook, which is this other packet here, I'm just going to give you 10 minutes to like sit with that before I throw in other notes with you. So the bottom right-hand corner is your page numbers. So on page 4 are 3 levels. At this point, you can do all the level 1s. I'm just going to go 10 minutes. So at 57, I'm going to post the answers. Just get done what you can in those 10 minutes. All right? Doesn't mean you have to do them all. If you want to just do the evens or the odds or try to get through them all. I'm looking to move on at 57. Division is going to be important when we start to do Pythagorean theorem and SOHCAHTOA, because with SOHCAHTOA you're looking at fractions, right? It's like opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Whenever you're looking at fractions, and those fractions might have roots in them, you have to do this thing called rationalizing the denominator. Someone somewhere one day a long, long time ago decided that you're not allowed to have roots in the bottom. Okay, that's what that means. So if you end up with a square root in the bottom, you have to get rid of it. All right, and the way to get rid of it is if you have a root in the bottom, then you just multiply it by itself. The easiest way to get rid of a square root is to make it a perfect square, and the easiest way to make something a perfect square is to multiply it by itself. So if I wanted to get rid of the root 8 in the bottom here, I could multiply it by itself. The rule is, though, if you do something to the bottom of a fraction, you have to keep it equivalent by doing that same thing to the top. So if I'm going to multiply the bottom by root 8, I have to multiply the top by root 8 too. Keep in mind that 1 and 8 in the top are not like terms. 1 doesn't have a root and 8 does. So technically this is like 1 root 8. I just don't need to write the 1. Alright, so I'm going to have it there just so you can see it, but eventually it's going to disappear because the 1 in front was just a placeholder number. And then the bottom becomes root 8 times root 8, which is root 64. And the square root of 64 is just a regular 8. So we have done this thing called rationalizing the denominator. We made the denominator a rational number. 8 is a rational number. Square root of 8 is irrational. It's got all these long decimals, all right? So once you rationalize the denominator, you still have to check to see if the numerator can reduce. So I would see if I could break up the 8. So are there any perfect squares that divide into 8? 4. So I could break the top up, and again, I'm not going to write the 1 anymore. So I'm going to break the top up into 4 and 2. And I'm writing this step out, square root 4 square root 2. You don't have to write that out. You can jump directly to 2 square root 2. Alright, so I'm breaking up that root. Now I have this number outside of the root and this number outside of the root. They're called like terms. I can reduce them. I can divide them. 2 divided by 8 is 0.25. But if I make that a fraction, it's 1/4. So I can change the 2/8 to a 1/4. And just like I said before, I don't have to write that 1. My final answer is the square root of 2 over 4. I can't do 2 divided by 4 is 1/2. Because 2 is in a root and 4 is not in a root. They're not like terms. So this is as far as I can go here. So if we're presented with a fraction and that fraction has a root on the bottom, we want to get the root out of the bottom. To get the root out of the bottom, we multiply the bottom by whatever is in the bottom. I'm just mirroring that root in the bottom. If I do that to the bottom, I just also have to do it to the top. 10 times the square root of 5 is not the square root of 50. They're not like terms, so I'm just going to write this as 10 square root of 5. And anytime you multiply a root by itself, it creates this perfect square. The square root of 25. The square root of 5 times the square root of 5 is the square root of 25, which is just a regular 5. I would see if I could break up the square root of 5 like I did the 8. But the only things that divide into 5 are 5 and 1, and neither of them are perfect squares. So my final step would be to combine like terms and say that 10 divided by 5 is 2. So my answer here is just 2 root 5. You okay so far? You guys remember this? It's been a while, probably. Alright, so the last one here on this row, I have a square root of 3 in the bottom. So I'm going to multiply by the square root of 3 on the bottom, which means I also have to multiply the square root of 3 on the top, because whatever I do to the bottom, I have to do to the top. This is going to create a square root of 9, which means the bottom's just going to become a 3. The top becomes 9 square root of 6. 9 square root of 6, because the 9 is on its own out there, and then I'm doing 2 times 3, so that's the square root of 6. And then I would see, can the square root of 6 reduce? Well, what are factors of 6? 1 and 6, 2 and 3. None of them are perfect squares, right? I'm looking for a 4, a 16, a 25. I don't have that, so my last step would be just to divide these like terms. 9 divided by 3 is 3. So my final answer would be 3 square root 6. If you have a root in the bottom, you got to get it out. I think the next few examples are just a little more complicated because they have these coefficients in front. It doesn't change the process though. Like for this one, if I have a square root of 8 in the bottom, I want to get rid of it. I'm not going to multiply by 5 square root 8. The 5 is a rational number. It's okay to be down there. The thing that can't be in the bottom is the square root of 8. So I'm going to multiply the top and bottom for this one by the square root of 8 to get rid of this part. So what happens to the bottom is the 5 that was rational is just going to stay a 5. I'm not doing anything to that. When I multiply the square root of 8 by the square root of 8 though, I get the square root of 64. So the bottom just becomes 5 times 8. I didn't touch the 5, I left it alone. We okay with that? Now the top is not the square root of 24, it's 3 square root 8. I can't do anything with that 3 and 8, they're not like terms. And we know that the square root of 8 is the square root of 4 and the square root of 2. I'm breaking up the 8. The bottom, 5 times 8 is 40. I'm just combining those like terms. Alright, so 3 times 2 square root 2 over 40. Just taking the 2 from the square root of 4 out. And it just becomes a regular 2. So then I have, I'll just bring this down here. Then I have 6 root 2 over 40. Now everything's rationalized. I simplified my roots as much as possible. The only thing left to do would be to see if these like terms reduce. And since they're both divisible by 2, that would be the final answer there. This one's, the next two, 15, 16, they're just more complicated because of those numbers in front. The process is the same. So if I have a root 10 in the bottom, I want to get rid of the root 10 in the bottom, and the way that I do that is multiply it by itself. And if I multiply the bottom root by root 10, I have to multiply the top by root 10. So the top becomes 6 times the square root of 200, 20 times 10. And the bottom becomes 9 times the square root of 100, root 10 times root 10, but the square root of 100 is just 10. Are you okay with that so far? So the 9 times the 10 becomes a 90. And I got this 6. Now for 200, if I wanted to split that up, I'd go y equals 200 divided by x, and I'd start with 200, which is in a perfect square, and I'd go down the list. The next number on the list is 100. 100 is a perfect square, so I'm going to do 100 and 2, splitting up the 200. So this becomes 6 times 10 root 2 over 90, or 60 root 2 over 90. And then I'm just reducing the 60 over 90. So 6 over 9 divided by 3 is 2 thirds. 60 divided by 90 reduces to 2 thirds. So I'm just combining those and reducing. Alright, so you guys try 18, 19. Save us some time from doing like that big column in the page, and let's just try 2 on your own. you work through those too, the answers are on the board, so you can just peek up and check as you go. Just know, this isn't like a one-size-fits-all method. Like, you can do this problem in probably 50 different ways. Like, some people reduce the root first, or they reduce the fractions first. I was just trying to keep it consistent because I know some people prefer steps, right? So I did it the same way every single time. Multiply by the root on the bottom, simplify the root on the top, then simplify the fraction, just so that the steps stay consistent. But you can get to those two final answers in different ways than the ways that I have on the board, right? So for the first one, or for 18, I got 2 root 5 over 45. And for 19, I got 3 root 6 over 7. Are you okay with that? I don't want to like move on too quick, because what we're going to do, the last thing we're going to do, is just the 2 final examples, the 3 final examples on this page, and they all involve conjugates. So it's the same idea, but it like ups the ante a little bit, because now you're working with not just one root on the bottom, but like a quantity, and you'll have to work with conjugates. You okay with that, Ryder? I don't want to do it if you're still working. Alright, so the last part is we're rationalizing with conjugates. So it's not going to be enough now to just multiply by root 6, because if I multiply the bottom by root 6, sure, it's going to create a perfect square here, but it's going to give me a 3 root 6 right there, and it's not going to get rid of the root, right? I'm going to have 3 root 6 plus 6, and there's still going to be a root there. So the only way to get rid of the root in the bottom for something that has a plus or a minus in the middle of it is to multiply by its conjugate. So remember we talked about with conjugates. In a conjugate, the first number is the same, the symbol is opposite, and the second number is the same. So the conjugate of 3 plus root 6 is 3 minus root 6. So if I want to get rid of the root truly here, I have to multiply by its conjugate, right? So I am multiplying by 3 minus root 6. If I do that to the bottom, I have to do that to the top as well. So I'm multiplying the top and bottom by 3 minus root 6. Multiplying by just root 6 isn't going to get rid of the root in the bottom. It's going to get rid of one root, but it's going to add another. This, you'll see, will get rid of the root in the bottom. So here's what happens to the top. The top becomes 4 times 3, which is 12, minus, because this is a minus symbol, 4 times root 6, which is 4 root 6. Okay, so I'm just distributing the 4 to the 3 and to the negative root 6. Now on the bottom, it's a FOIL, because it's a binomial times a binomial. So I'm doing 3 times 3, that's 9. And then 3 times negative root 6, negative 3 root 6. 6 positive root 6 times 3 is positive 3 root 6, which you'll see those are going to cancel out. And then positive root 6 times negative root 6 is negative root 36. So just like we were doing earlier, when you multiply by the conjugate, what happens is the middle term zeroes out. The negative 3 root 6 and the positive 3 root 6 become 0. And the denominator ends up being, so the top is 12 minus 4 root 6. And the bottom ends up being 9 minus 6, because the square root of 36 is just 6. Right, so the middle term zeroes out, and the last term is a perfect square. So now we've rationalized the denominator. There's no more root in the bottom. So let's see what we have. We've got 12 minus 4 root 6 over 9 minus 6, which is 3. Now, if all of these numbers, 12, 4, and 3, were divisible by the same number, I could reduce this, right? Like if they were all even, I could divide them all by 2. If they were all divisible by 3, I could divide them all by 3, but they're not. Like I can divide 12 by 3, but I can't divide 4 by 3. can divide 12 by 4, but I can't divide 3 by 4. So because those three terms don't have like terms or common factors, this is done. I have rationalized the denominator because there's no root in the bottom. So if I want to do that same process to 21, because it's a binomial and they're not connected, like if this was just 3 root 7, I can multiply by root 7. But because there's a minus in the middle, I have to do the conjugate. So conjugate is keep the first number the same, make the middle sign opposite, keep the second term the same. So the conjugate of 3 minus root 7 is 3 plus root 7. And I'm going to do that to the top and bottom. Same exact thing. So the conjugate of 3 minus root 7 is 3 plus root 7. So 6 times 3 is 18. And 6 times root 7 is positive because it's plus. 6 root 7. I'm not calling that root 42. Can't multiply that. Right? The bottom is FOIL though. So it's 3 times 3. 3 times positive root 7, we'll call that plus 3 root 7. Negative root 7 times 3, so we'll call that minus 3 root 7. Negative root 7 times positive root 7 is a minus. Negative times positive is negative. And 7 times 7 is going to be a root 49. What happens here when you multiply by the conjugate is that middle term cancels out. You can start to just not write it, right? I'm showing you it because it's a toolkit and you need to see all the steps, but this is always going to cancel out. And you're just going to be left with the first and last terms. So you can start skipping those steps. I'm not doing it for your note's sake here. So the top is 18 plus 6 root 7. The bottom becomes 9 minus 7. The square root of 49 is a perfect square. So I've got, now this one can reduce because 18, 6, and 2 all share a common factor. What can I divide them all by? 2. So I'm just going to divide each of them by 2. 18 divided by 2 is 9, plus 6 divided by 2 is 3. It just still has a root 7 on it. And 2 divided by 2 is 1. I could write over 1, but I'm not going to. That's the final answer. This fraction here is the same as this fraction here. If I typed in my calculator 6 divided by 3 minus root 7 and hit enter, I get a really weird decimal because it's irrational. But if I typed 9 plus 3 root 7 in the calculator, I get the same really weird decimal. They're equivalent fractions. They're equivalent terms. One has a root in the bottom and one doesn't. All right, so you try, this is the last example we're going to do. You try to rationalize that one. The 4 in front doesn't make a difference, okay? Your conjugate is 3 minus 4 root 3. The first term stays the same, the second term stays the same. The only thing you do is put a minus there instead of a plus to get the conjugate. I'm gonna do this one on a different slide in more detail, cause I just kinda skipped some steps here. I don't believe those coefficients have common factors, cause 20 goes into 5, 15 and 20 go into 5, but 39 doesn't. 15 and 39 go into 3, but 20 doesn't, so I think when you get to that point, you're as far as you can go. Have you ever learned that? I always wonder if that's new or not. Does that look like something random? I don't think you learned that. That is a SAT concept. Like that is something that shows up on the SAT. So we haven't always done it in pre-calc, but we added it in recently just because you guys still probably need to take the SAT or will take the SAT. So I've got this, it's not something I'm going to like collect or check, okay? It's just if you wanted extra practice and to stay on top of these things, you've got those 2 level tiers that we didn't do. If we did level 1, we went over it, but we didn't do 2 or 3. They're there, the keys on Canvas. You can or cannot do it. I'm not gonna check it, it's there for you. If we're getting close to the quiz and you want extra practice, it's there, all right? Tomorrow we will do Pythagorean theorem, which should be pretty quick because we have already went over that recently, and then we'll do special right triangles, and then Friday will just be a practice day of everything we did this week. So nothing new on Friday. Questions for me? We're good? Okay.